Hello, this is Pat Kelly.
Okay, in this problem, they ask us to use Greens Theorem. So I'm already excited that we get to use Greens Theorem, but we're supposed to do so in order to find the work that this force, of course they give us a force function, the work that that force would put on an object that we're traveling around a path here. You can see I've drawn it, my x squared plus y squared equals 1 path for this particular problem. I'm going counterclockwise around that, okay? So to get started, if we're going to use Greens Theorem, that means that I can jump right into my integral for work here. It's going to be the double integral over the region. And then the cool thing about Greens Theorem is all you do is a couple of partial derivatives, and subtract them. It starts like this, is the partial of n, which is always here, with respect to x, which is just going to be a 1. Subtract the partial of m with respect to y. So the partial here with respect to y is just x. See why Greens Theorem is so cool? Our integral becomes pretty small and manageable. For the most part, manageable. For the most part, manageable in this particular problem, because now what I'm looking at is this dA, that differential element of the area. That's why I like my drawing. I like to have that in front of me as I can visualize what's going on. And what I might not like so much in this case is that that area is not clearly defined in terms of y as a function of x, or even x as a function of y. You don't have good tops and bottoms and lefts and rights so much. Not as much as if we convert this to polar coordinates. Okay? An old skill maybe, but definitely a good one to have up your sleeve is let's do just a little bit of work to put this path in polar coordinates. Right? Hopefully you remember with polar coordinates here, your x just equals r times cosine of theta. And your y just equals r times sine of theta. Probably harder to remember, but you will end up using what does dA equal with polar coordinates, and that's going to be r dr d theta. Okay. With that little flashback from the past there, a blast from the past, it's going to give us stuff to plug in for this integral and make it behave very smoothly. So let's get to that. So this integral now equals, it's going to be a double integral still, and then 1 minus the x. I want to get in terms of my r's and thetas, so I look over here, and x is r cosine of theta, and then times dA, which is this r dr d theta. And I paused a little bit even when I wrote the integral signs down, because you want to think about your limits of integration now. The first variable that I'm integrating with respect to here is going to be r. And so the limits there, it starts at 0 and goes to 1 for this region of my unit circle. And for the theta, it's going to start at 0 and go to 2 pi for the full circle. Okay? All right, now everything's in terms of r's and thetas, and we're ready for an integral, a double integral here. Let's get to that. 0, 2 pi. Integrating with respect to r first, that's just going to be r. Let's do the integration. I was going to distribute through first. The r would have to multiply, but I'm just going to get an r there. So r squared over 2 minus cosine theta is just a coefficient if I'm integrating with respect to r. I do have r times r, so r squared is going to go up to r to the 3 over 3 times that coefficient of cosine of theta. And I have to evaluate all of that as r goes from 0 to 1, and then there's still going to be that d theta. Okay, so this equals 0 to 2 pi still. Gotta love zeros and ones, right? For r, if I plug that in here, I'm just going to get a 1/2 minus a 1/3 cosine of theta. Plug in a 0, that's all going to blank out. So our integral is looking pretty manageable, I think. And so let me slide over this next step. Integrate this with respect to theta, and I'm going to get theta over 2 minus cosine theta is just going to go to sine, right? So you'll have a 1/3 sine of theta that I need to evaluate from 0 to 2 pi. Slip down here. I think this probably can be my last step if I do this right. Put the top number in, the 2 pi. 2 pi over 2 is just going to be pi. Subtract the 1/3 times sine of 2 pi, and that's 0. And then subtract what happens when you put in the lower limit of 0, and that's just going to be a 0 here. Subtract is plus 1/3, but times the sine of 0 again, so there's a 0. The sine of 0, which is a 0 again. Looks like all of this is just going to be a pi. All right, not bad. Okay, that's my answer for this one. Practice some more on your own. I know you'll do well.